right, so we're going to go ahead and do another example using those same properties, but this time we're actually going to apply it to a differential equation. So, even if you understand how to use this translation property or its inverse in isolation, it's another thing to see it like as it arises naturally in a differential equation. So our problem is going to be y double prime minus 6y prime plus 9y equal to t squared e to the 3t, with initial conditions y of 0 equal to 2 and y prime of 0 equal to 17. And so from last week, hopefully you kind of are looking at this problem and can already think in terms of how we solve it with Laplace transforms. And that's going to be to take the Laplace transform of both sides and set them equal to each other. So we'll have L of y double prime minus 6y prime plus 9y equal to L of t squared e to the 3t. And at this point, you all should be really comfortable with taking this approach. If you're not, you really need to go back and review last week. So if we've got, let's go ahead and do the left-hand side first because it's more familiar to us. So it should go more quickly. If we're trying to take that Laplace transform, we're going to use derivative rules and linearity. And we'll find s squared capital Y minus sy of 0 minus y prime of 0 for y double prime minus 6sy minus 6 times sy minus y of 0 plus 9 capital Y, or s squared y minus 2s minus 17 minus 6sy plus 6 times 2 is 12 plus 9y. When we plug everything in and just do some algebra to distribute that minus 6 times sy minus y of 0. And then because we know that eventually we're going to have to solve for capital Y on one side and everything else on the other, let's go ahead and factor out. We're looking at s squared minus 6s plus 9 are all the things that are multiplied by y here. And then everything that's left over is a minus 2s minus 17 plus 12, so minus 5. And then we can also go ahead and note that s squared minus 6s plus 9 is just s minus 3 squared times y minus 2s minus 5. So all of that is review from last week, and I went through it kind of quickly because this problem is going to be long. The right-hand side, L of t squared e to the 3t, is the part that's related to what we are learning in this video. So we've got our I should rearrange this in the order that you're used to seeing it. That's L of e to the 3t times t squared. So that's our A is 3, and our little f is t squared, so our capital F is L of t squared, which would just be 2 factorial over s cubed. I'll go ahead and put my A equals 3 a little further down too. So we know that L of e to the at f of t is capital F of s minus a, but our A is 3 and our capital F is 2 over s cubed. So this is just going to give us 2 over s minus 3 cubed. And then since we've taken both sides of the equation, the Laplace transforms, we can set everything equal. So we've got s minus 3 squared times y minus 2s minus 5 should be equal to 2 over s minus 3 cubed. Or solving for y, we've got s minus 3 squared times y is equal to 2 over s minus 3 cubed, plus 2s plus 5. And then we divide by that s minus 3 squared on both sides. So we've got s minus 3 squared, and then that s minus 3 cubed becomes an s minus 3 to the 5th when we divide by that s minus 3 squared. So all that was algebra to solve for y. And so that's kind of like the forward part of the problem, where we start out with the Laplace transform of both sides, and then we solve for capital Y. And eventually what we're going to want to do is take the inverse Laplace transform to find little y would be the inverse Laplace transform of everything. Just like that. Where little y is the solution to our differential equation. So hopefully that approach feels familiar from last week. But what we're going to have to do before we can take that inverse Laplace transform is use our new property to rearrange the quantity inside the curly braces here in a way that we actually know the inverse Laplace transform of. It's going to take a little bit of space. So we're going to move over here to the next slide. And we're looking at y is the inverse Laplace transform of 2 over s minus 3 to the 5th plus 2s plus 5 over s minus 3 squared. And so the first thing we're going to think about is we see s minus 3 all over the place. So maybe we're going to use our f of s minus a property again. Or just as a general rule, if you use a property in the forward direction of the problem, you're going to have to use its inverse in the backwards direction of the problem. So we need this to look like f of s minus a, where a for us is 3, so f of s minus 3. So we're looking at L inverse of 2 over s minus 3 to the 5th. That part's fine. And then the s minus 3 squared in the next part of the problem also looks fine. But then the numerator right here, 2s plus 5, we have that problem again where we need it to look like s minus 3, not just s. So we want to have an s minus 3. Again, we add the 2, but that's 2s minus 6, and we want it to be plus 5, so that's how we had that plus 11 before. So we go ahead and write it like that. And then from here we can go ahead and use linearity to start thinking about actually computing this inverse Laplace transform. So we've got L inverse of, equals 2 L inverse of 1 over s minus 3 to the 5th plus 2 L inverse of s minus 3 over s minus 3 squared plus 11 L inverse of 1 over s minus 3. Actually, we're running out of room there. So what we'll go ahead and do first is break it up inside. L inverse of 2 over s minus 3 to the 5th plus 2 s minus 3 over s minus 3 squared plus 11 over s minus 3 squared. And in our next step, we're going to cancel out that. So we're going to have equals 2 L inverse of 1 over s minus 3 to the 5th plus 2 L inverse of 1 over s minus 3 plus 11 L inverse of 1 over s minus 3 squared. I don't know if you can hear that. That cat really wants to go for a walk right now. So what we're going to be using is our inverse property. I wrote it here. L inverse of capital F of s minus a is e to the at little f of t. So remember, our a equals 3. And we just have to identify what our capital F is going to be in each of these cases. So here we've got that our capital F would be like 1 over s to the 5th. Right here, we actually don't have to worry about the problem. And right here, we've got our capital F would be 1 over s squared. The reason we don't have to worry about the middle one is because we just know that that's e to the 3t. We knew how to do that earlier in class. So for the other two, though, for an f that looks like s to the 5th, what we're looking at is a t to the 4th, where it would be like f is 4 factorial over s to the 5th. And for an f like 1 over s squared, we're looking at an f equal to t to the 1, where capital F is 1 factorial over s squared. So if we want this to look like 4 factorial over s minus 3 to the 5th, then what we're going to have to do is just divide by a 4 factorial out front. But our 1 factorial over s minus 3 squared is okay the way it is. So this is our f of s minus 3 for f equal to 4 factorial over s to the 5th. So what we're going to have is our 2 over 4 factorial. L inverse of 4 factorial over s minus 3 to the 5th is just going to be e to the 3t t to the 4th plus 2e to the 3t plus 11. L inverse of 1 factorial over s minus 3 squared is going to be that e to the 3t from the s minus 3, and then just use our regular little f, which is t. And if you want to simplify this, oh no, our video is already very long. We're going to have y equal to 2 over 4 factorial is just 1 over 12, e to the 3t t to the 4th, plus 2 e to the 3t plus 11 e to the 3t times t. And that would be the solution to the differential equation right there. I'm going to go ahead and stop here, maybe make some notes in the next video about this.